Okay, I'd like to extend a warm welcome to everyone to the Knime Big Data Workshop, which is part of this year's extended Knime Online Summit. My name is Björn Lohrmann. I'm a Big Data lead developer here at Knime, and together with me is my colleague Tobias Kötter, who will also be giving this workshop to you. Before we start off, I would like to highlight that you can use the Q&A section in Zoom to post your questions and also upvote questions that you find important. Also, this session is recorded and it will be available on YouTube as a video. And also video and slide deck will be available on our website shortly after the workshop. If you happen to not know how to use the Q&A tool in Zoom, at the bottom of your Zoom window, there is the Q&A button. And if you click on it, it opens a window where you can ask and upvote questions. Okay, and another second thing before we get started is a little bit of advertisement. I'd like to mention that there's a lot of learning materials on our website, and especially the Knime Press course books can be downloaded there. And there's, for the attendees of this workshop, there is a promo code that allows you basically free download. The promo code is valid for 2 months. Also, secondly, there are a few more courses taking place as part of the Knime Online Summit 2020. On May 18th, there will be an introductory course on text processing held online, and on May 25th, there will be an introduction to big data with Knime Analytics Platform, which covers basically the workshop materials in a little more depth and with more interactive exercises. Okay. Also, there's a promo code where you can get 20% off of the training courses. Again, the slide deck will be on our website, and also if you need the promo code after this, it'll be part of the Q&A section as well. All right. So I'd like to briefly say that the target audience for this workshop is mostly people who know analytics platform, Knime Analytics Platform a little bit already. So we won't be covering Knime basics. Instead, we'll be mostly diving into the details of the Knime extensions that deal with big data and show you how to use them and show some examples. First, I'd like to briefly define what big data means, and then we'll dive into Hadoop and Spark and all the various extensions in Knime that are built around this. Okay, so what is big data all about? Well, there are kind of two traditional definitions of big data. One of them is that big data is a whole field that deals with ways to analyze and extract information from data sets that are either too large in the sense of too many rows, or too complex in the sense of too many features in order to be dealt with by traditional data processing application software, which is a way of saying relational databases or Excel or like desktop applications that we've been using so far. So this is mostly a volume thing here, which makes the traditional software inapplicable, and you need special purpose tools. The other perspective on what big data means is that the aspects that make big data big are not only volume, but also varieties. So a lot of different types of data, whether that is standard tabular data or text or images, audio, time series, and all these things. but also big data deals with fast data, so velocity is an aspect. And in typical big data applications, data is produced continuously and pretty fast, and so you kind of have to keep up with it. And this brings us to what is the goal of big data technologies. It is to enable predictive or other kinds of advanced analytics to extract value from such data. Knime analytics platform by nature is very open, so it really nicely allows you to deal with especially the variety aspect of data. So we have a lot of integrations with, for example, platforms that allow you to execute computation, whether that is Hadoop or Spark or H2O, but also you can connect to many data sources to pull in data or write it out, whether that are relational databases or Cloudera and the Cloudera platform with Impala or Hive, for example, or cloud platforms that also have a huge variety of different data storage systems that you can use. On the other hand, there is we have integrations for other external tools that allow you to enrich the Knime experience with features of that particular, for example, programming environment. I'd really like to highlight the Python integration here, which is really nice because it allows you to reach out to all the existing Python libraries, which are really popular in the data science domain. Okay. All right, so let's dive a little bit into Hadoop and Spark first. So Hadoop, Apache Hadoop is an open source project hosted under the Apache Foundation, and it is designed for distributed storage and processing of large data sets. That usually requires that you employ up to thousands of machines that work in conjunction to solve one big data problem. The roots of Hadoop go back into the year 2006, where it was made an Apache project, and it goes even further. If you look at the history of Hadoop, it goes even further back to Google technology, which was, so there was this paper in 2003 published by Google on the Google file system, and Hadoop, the Hadoop file system HDFS then kind of became the open source version of the Google file system. Apache Hadoop was really influential in the way that it spawned this really large ecosystem of products and other projects. So systems like Hive and Impala, or the Cloudera product set, for example, is really built around Hadoop, and Hadoop is kind of at the core of this, and still is. So how would you kind of split up the Hadoop and the surrounding ecosystem? So I'd like to look at this in terms of layers. And layers here means that lower layers provide a service that is used by the upper layers. And on the lowest layer, you have storage. And the storage system that is main storage system provided by Hadoop is HDFS, which offers a file system that is really scalable, allows you to store large amounts of data over a large cluster of machines. And it deals then with all the problems, the technical issues that arise when doing that. And we'll now be going kind of from bottom to top and look at each layer briefly to get a basic understanding of what the function is. So let's start with HDFS. HDFS stands for Hadoop Distributed File System. The idea of HDFS is that it's supposed to store really large files across a large number of machines. To do that, it typically splits up large files into smaller chunks. These are called blocks. Typical block size is 64 megabyte, but all of that is configurable actually. And then these blocks, they get spread out over the different machines in the cluster. So basically, this file is being chunked up, and bits and pieces of it are stored everywhere. So when you do that, you kind of need to deal with machine failures. So what must not happen is that when one of these machines that has a block, when it fails, for example, the disk crashes, that you're going to lose data, or you're going to lose all the blocks that are stored on that particular machine. So part of the HDFS design is are ways to deal with this. And the major way is data replication. So each block is then replicated usually 3 times over the whole cluster. So when a single node or even 2 nodes fails, you'll have at least a third node that is guaranteed to still have that the last remaining block of this particular file. So this is kind of improves data reliability, but it also increases availability of the whole system, and it's a nice way of distributing load also, because then you can do parallel reading of these blocks, so you get a much better load distribution inside the cluster. Going up the stack a little further, there's Yarn. So Yarn is a bit kind of abstract for the non-techies. So Yarn is what's called a cluster resource management system, and the way this is designed is that you have, much like in HDFS, you have these nodes that store data on the same machines. You have services that basically manage the CPU resources and the memory of that particular machine. And then there's one central machine which has the resource manager running, and that one decides when an application comes in and wants to request some resources, where these are going to be reserved. And the general idea there is that Yarn allows you to move the computation. For example, a SQL query that you're running via Hive. Yarn will schedule this, the processing of that SQL query to particular nodes, and typically it'll be those nodes that also store the data that's being processed. All right. The traditional processing scheme of Yarn is MapReduce. So while MapReduce itself is outdated, many of the underlying principles do still apply. So I'd just like to briefly explain to you the mindset, or the basic idea of MapReduce, because that idea is still everywhere and you still find it in Spark. Spark is basically just an extension of what MapReduce can do. So in MapReduce, when you have a large chunk of data, which is here on the left side, so first you need to solve a problem with that. Okay, here on this particular slide, the problem is you want to do word count. So you have a lot of words in your data, and for each word you want to get the word count. So the way to solve this with MapReduce is that you would write a MapReduce job that is basically performs the computation here, and MapReduce will split up the processing into different phases. The first phase is the mapping phase, where on the basically on the blocks in HDFS that we've seen, each of those blocks has a certain amount of words in it, and mapping would kind of read this block, parse out the words from that, and assign the count 1 to each word. So because you're doing this in parallel on different machines and in parallel on all the blocks, you'll get a lot of duplicate words that have the value 1 assigned to them. So for example, the word blue appears in this particular block, but also in this one. So because MapReduce, the next step here is then that you would shuffle all these different value pairs over the word. Shuffling means you're kind of doing a grouping operation. Okay, I'm hearing that the video is either paused or stopped. What I can do is I can stop sharing and reshare. I hope the video is back now, or the screen sharing is back now.
We can see your screen, but not your video.
Okay, yeah, it seems, yeah, Zoom is refusing to start my video. When I click, nothing happens. Okay, well, then we'll have to do without, I guess. All right, so during the shuffling phase, all these different records get grouped by word. And then in the reduce phase, each reducer gets all the records that have one particular word in them. So this one does get the word blue. And then it can do the actual counting because it only sees, and that scales very well. All right, so the last thing I mentioned is the reducing phase that basically counts each word, and then the result is aggregated again, so you'll have this final word count. So the basic idea here is based on these blocks to parallelize the data processing. There is kind of this embarrassingly parallel phase, which is the mapping, where you can process each bit of data independently from one another. But in most useful applications, you need to perform some kind of aggregations. So that's why there's also this shuffle and reduce phase, basically to do aggregations like word count. All right, going up the stack a little further, you'll typically find systems like Hive. So Hive in particular is a SQL database on top of files that are stored in HDFS. So these files, they can be CSV, or they can have other special formats that are that you typically find in the big data domains, such as ORC and Parquet. Hive, as a SQL system, essentially it allows you all the things you can do with SQL, such as data summarization, currying, and analysis. So the thing that is a little unusual is that it does not have its kind of own internal storage format, but it really only takes these files, which are stored in HDFS, and it you either have to give it schema information, or it extracts schema information from it. So that allows you to have a really kind of database, relational database view on top of plain files in HDFS. The way Hive then runs the SQL queries is that it translates the SQL query into a sequence of jobs that run on Yarn. So traditionally this was MapReduce, but nowadays in Hive you'll find other systems like Tez and Spark that kind of do the heavy lifting of computation. Again, the principles here are kind of the same. So these Tez and Spark are designed for parallel computation, really. So this is how Hive then kind of runs your query. All right. And the last system I'd like to mention is Spark. Spark is a cluster computing framework, which is, you could call it a generalization or extension of MapReduce. That's because originally it was measured up against MapReduce in the sense that it was designed to be a lot faster than MapReduce. And the deciding factor for Spark's speed is the fact that Spark uses in-memory computing. So in many cases where MapReduce has to go back to the HDFS file, Spark already has data cached in memory and can just use it there. So it loses a lot less time on data loading. Spark itself has a purely programmatic interface. So you need to be a developer in either Scala, Java, Python, or R to make use of Spark. And the things that you can do really well with Spark that you can't really do well with MapReduce are iterative algorithms, and you'll find a lot of those in the data science domain. Like typical data mining algorithms need to go several times over the data, so this is what's called an iterative algorithm. Also, it's really good at interactive data analysis. This is due to the fact that Spark does in-memory computing. So it can just pull data from in-memory really quickly, which is really nice if you have a human in the loop that just really wants to peek into the data. All right, the underlying data representation for Spark are data frames. So data frames are table-like structures. So they're a table or a data frame is a collection of rows, and it has columns. And the columns have types. So that's relatively well known. Data frames are also immutable, which means that you cannot change what is inside a data frames. The only thing you can do is you can apply a transformation on it that creates a new data frame, which has then different data inside of it. Also, one very interesting aspect is lazy evaluation. So when you perform these transformations on a data frame, these transformations are not executed immediately. So the only situations where Spark will actually perform computation is when you trigger certain operations, which are called actions. And these actions, they typically are of the kind that really need to see the data. And the last aspect I'd like to highlight here is that a data frame is distributed by nature. So each data frame is split up into partitions, and a partition is stored on a particular Spark executor, which runs on one particular node inside your cluster. So you won't find the data frame data typically on one node, but it's spread out, which makes it a really good basis for parallel computation again. I'd like to talk a little bit more about lazy evaluation, because that is one of the concepts that is a bit unfamiliar for users of the traditional Knime analytics platform nodes. So as I mentioned, there are these transformations, and a data frame is internally really just a sequence of transformations that are applied on some initial data frame. And the actual execution is then triggered when you do an operation that needs to see the data. On this particular slide, there's a little workflow that first reads a data frame from a Hive table into Spark. So these black rectangular ports are Spark data frames. And then it performs some pre-processing on this data frame. At each step here, you see these ports, and every output port is essentially a new data frame with transformed data. But actually, up until this point, the partitioning, nothing has actually happened. So Spark hasn't performed any computation. Only in the next step, in the Spark decision tree learner, where you tell Spark to learn a model, then it actually has to go to the data, and then it will see, okay, I need this particular data frame. Okay, to compute that, I need to go back to the sorting phase. Okay, to do the sorting, I actually need the filtered, column filtered data frame, and so on. And in the end, this will lead to data being read from Hive. And then all these transformations get applied ad hoc, and the model gets learned on that. So this is sometimes why when you're using the Knime Big Data extensions, some nodes will be really fast to execute, and some nodes will take a little longer. Typically, the longer ones are those that that trigger an action. Okay, to work with Spark, the first thing you always need is a Spark context. The Spark context is the main entry point for working with Spark, and for Knime, it really kind of represents the connection to a Spark cluster. Also, there are a few things attached to a Spark context, such as resource allocation of the cluster. So when you open up a Spark context, Spark will go to Yarn, and it will ask for resources on the cluster. So it will say, I want 50 different 50 containers with 6 cores and 20 gigabytes of RAM each. And then Yarn will try to see in the cluster where those resources are free. It will create those containers. It will start Spark inside those containers. And then basically this initial piece here, it ties everything together, and it's orchestrating the computation. Okay. So at this point, I think is a good point to do a little bit of Q&A and question answering. If there's anything that is better answered live, I'll take a brief look. Or if you have any question right now about Hadoop and Spark, go ahead and ask it. I think I'll give everyone 1 or 2 minutes to ask some questions.
Okay, so there are quite some questions now in the Q&A. Let's see. Okay, the first one that I pick is this execution is done in Spark rather than in Knime itself. Yeah, that's absolutely true. So all the execution is pushed down into the cluster. The Knime nodes themselves only orchestrate the execution, basically. So the data or the execution is done where the data lives in the big data cluster then. Do you also want to take one, Björn? Or?
Yeah, I'll take one. So the question I'd like to answer is, what is generally used for installation of the ecosystem? Typically, what you do is you don't install all these services manually, but you go to one of the vendors. Right now, there are two major vendors left, I would say. One of them is Cloudera, which has CDH, which is their traditional on-premise platform, which contains all of the Hadoop's own services, but also Spark, Hive, Impala, HBase, and a whole variety of other services. So these are pretty big, I have to say. But they have really convenient tools that do the setup for you, and so you don't have to deal with individual service configurations all the time. There's also MapR, of course, which is kind of in the same domain. The other approach you can take is you can use a more managed service. So the one I'd like to highlight here is the Databricks platform. So the Databricks platform provides a sort of managed Spark service, and it has its own kind of file system. The Databricks platform does not contain really Hadoop at all, but it's built around Spark, and the file system is the Databricks file system. It's called DBFS, but it's a kind of equally scalable. But it's a fully managed solution, so you kind of just really have to make a few clicks, and you have a cluster that's either running on AWS or Azure. That's kind of the idea there. Cloudera's CDP is kind of going into the same direction of having a more managed solution. CDP is the successor of CDH on the Cloudera side, but there's lots of more. So there's Google Dataproc and Amazon EMR, which are kind of managed traditional Hadoop environments. So these are also kind of nice because you can pull up a cluster with just a few clicks, and you just say, okay, I want Hadoop, I want HBase and Spark on it, or Hive on it, and it will instantiate that for you within a few minutes. Okay. Tobias, you want to take the next one?
Yeah, maybe I can take do you need to have Spark and Hadoop run locally? For trying out and experimenting with all of the nodes, Björn will show the create local big data environment node, which is a really nice node that spins up a local Hadoop cluster, so to speak, on the machine Knime is running. So if you just want to try it out, just use this node, as Björn will show in some minutes. Okay, that's done. Do you want to take the Spark and Databricks the same or different? Or?
Yeah. So
okay.
So Spark is by itself an open source project, really only. Databricks is and these big open source projects, they often have companies behind them that push them. Knime being one of those. And there's a similar relationship between Databricks and Spark. So Databricks is the company that is pushing Spark. And there's this Databricks platform, which contains Spark, a really well-managed Spark service, but not only. So they're getting more open now and integrating also different platforms like TensorFlow, but also you can run arbitrary Python code on there. So Databricks tries to get a little broader than just Spark and big data. Yeah.
Okay, maybe I can take the use performance gain in Spark. To use the performance gain in Spark, is it necessary partitioning the data? Yes, I mean, if you want to make use of the parallel computation or parallel processing, your data needs to be partitioned and split up across different worker nodes. Otherwise, all the computation will be done only on the node where the data is present. So yeah, partitioning is a very important thing to take into account. And that's why in Knime you also get the information about for the Spark data frames, how many partitions they have, and you also have the option to do repartitioning whenever you want to by using the special Spark repartitioning node. So shall we move on?
Next one is what is the difference between Hive and Impala connectors? Hive and Impala are two different systems that solve relatively similar problems within the Hadoop ecosystem. So they both offer a SQL front end, so you can run SQL queries on them. And within Knime, they both look like more or less normal SQL databases. It's just that there are different systems and they have slightly different capabilities. So traditionally, Hive was more for the kind of long-running analytical queries and data warehousing use cases, whereas Impala used to rather address the kind of OLAP, where you kind of ran queries and you wanted quick answers because there was a human in the loop sitting in front of it. This has changed a little bit, so they've become more similar, I would say. So there's this thing called Hive LLAP now, which was introduced with Hive 3, I believe. So Hive LLAP is basically, it tries to give you the same experience as Impala in the sense that it gives quick answers. Yeah, also they have slightly different capabilities in their SQL dialects, but I think the major one is really kind of the mindset and the approach here. Yeah. Okay.
So I think we should continue with the slides.
Yep, agreed. Okay. So let's dive into the first Knime extension, which are the Knime Big Data connectors. The Knime Big Data, to understand the Knime Big Data connectors, I would briefly introduce the general database extension, because that's what most of the Knime Big Data connectors are built upon. So the standard Knime database extension allows you to visually assemble complex SQL statements and connect to basically a variety of databases that offer JDBC compliance. So you need the JDBC driver. The typical step when you make a database workflow in Knime is that first you need a connector node, which wraps the driver and which provides this database session port. Inside that driver, for example, also you would put in authentication information, or well, in the SQLite case here, which is a file-based database, you would put in the file name. So these connectors are really specific to the particular database. Whereas the other nodes that you attach to the connector, they are database agnostic. So they are designed in a way that they don't really make a difference. Doesn't really make a difference whether you run them on Hive, on SQLite, or on Oracle. You would use the same workflow or the same nodes and with the same parameters. So there's a whole set of data manipulation nodes for the database extension. So you find the usual things like row filtering, grouping, joining, column filtering, and so on. So the important point here is that all these operations are performed inside the database, and Knime really just with these nodes, with these data manipulation nodes, it builds a complex SQL statement. And it will really only effectively run that SQL statement once you start looking at the data, or when you write out the data to someplace else. And that brings us to the last step, which is kind of exporting the data. So there are various ways of doing that. You can save a query result into a new database table, or you can read the query result back into Knime. In both these cases, this would be the actual point where the query is being run. So this also has kind of this lazy behavior that I've mentioned with Spark. All right, so the Knime Big Data connectors, as I mentioned, they're built upon the database extension, and they include drivers for Hive and Impala, and also Databricks. They contain HDFS connection nodes, which allow you to access HDFS as a file system. So the HDFS connection stuff is not integrated with the database nodes. This is for the remote file handling nodes in Knime. But most of the the biggest part of the connectors are actually the database connectors here. So on the right-hand side here, you find the most prominent ones that I mentioned. So the Databricks connector is a little bit special because it's an all-in-one node that at the same time provides you a database connection, a file system connection, and Spark. That is because when you have a Databricks cluster, you have all these things anyway at the same time, and they're integrated with one another, so it doesn't make sense to kind of split this out into separate nodes because you need everything all the time anyway. Okay, the Hive connector, I'd just likely briefly look into it. It creates a JDBC connection to Hive. It allows you to connect to unsecured and Kerberos secured clusters. There is sometimes the need to register proprietary JDBC drivers. So for example, the big data vendors like Cloudera, they provide proprietary drivers for Hive and Impala. These you can register in Knime. And we'll take a closer look at this, but I just like to highlight that there's this preference page that deals with that in particular. Often you also have the problem of getting data into these database systems. For that, we have the DB loader node that can be connected to Impala, also Hive, and the Databricks node. Typically, this for the big data environments, the DB loader will require a file system connection as well, because the data that you upload from Knime, it's first uploaded to a file system such as HDFS, and then we run the node runs SQL queries to import that data, which is already in HDFS, into a Hive table, for example. All right, that brings us to our first demo, which is the flight delay statistics workflow. This workflow is also on the Knime Hub. The link is on the slides. Okay, so I'd like to show a few things here. So this workflow connects to a Kerberized Impala instance, and the way you would do this is that you select the Kerberos authentication option, and depending on the driver, then you need to specify certain JDBC parameters. So these here are specific to Cloudera's proprietary driver, which I've registered beforehand. I won't dive into much detail what they mean, but there is documentation in the node description of the Impala connector, which options you will need. So the ones I've used here are the proprietary Impala driver options, but for the embedded driver that we ship, though this one would have slightly different options there. In terms of the driver registration, just very briefly, you would go to File Preferences, and then in the Knime section, click on Databases. Here you can add entries that basically define a JDBC driver for the Knime nodes. The important thing is to specify the database type. So for the Impala connector to pick up the driver, you have to set the type to Impala, and you have to specify the driver jar file that Cloudera provides. Okay. So once you have connected, so this workflow then first loads some data. The data is open airline delayed data. So if we briefly look at it, it's it's flight delays with timestamps basically, and you have arrival delay and departure delay. Those are the most important ones here. This workflow then creates a new database table in Impala, which is called airline. And then uploads this local data into the cluster using the DB loader node. So here, the DB loaders itself, the dialog is relatively simple. You just need to tell it into which table to upload and where in the remote file system to put the data. Once you have data, you can query it. So in this little workflow, what we do is we first select the airline data table, and then we group by day of the week. And we do an average aggregation on the arrival delay and an average aggregation on the departure delay. Then we sort again by day of week. So we get a nice table that gives us the day of week and the average arrival and the average departure delay on that particular day in minutes. And then with the standard Knime nodes, you can, of course, also visualize this. In this particular case, we can see that apparently on Saturdays, which is day 6 of the week, we have the highest departure delay of planes, but many of the planes still manage to catch up on the delay. Whereas during the work week, delays tend to be a lot lower, and surprisingly, a lot of the US airlines manage to be even a little earlier. Okay. Going back to the slides, I think we do have a little time for questions also. So if you have any questions you want to ask, now is a good time. I'll give you 1 or 2 minutes to. Okay, so there's one question here which I'd like to answer, which is whether you can create a local prototype of a workflow and then productionize it by swapping out the connector node with a real one. Yes, you can do that. So we have this create local big data environment node that allows you to do exactly that. Create local big data environment gives you a Hive JDBC connection, but also Spark and local file system access. With that, you can kind of prototype workflow on small data sets and run it locally on your machine. And when you're happy with the result, you can swap it out for a real cluster connectors, such as the Hive connector and, for example, the create Spark context Livy node, which we'll see later on as well.
Maybe I can also answer another question, the Neo4j question. So the question is there an option to connect to a graph database such as Neo4j? They recently made a JDBC driver available to make SQL calls to Neo4j, and I didn't see it in the list. Yes, so we don't have a dedicated Neo4j connector as of now, but you can register any other JDBC driver in Knime. Just follow the steps that Björn has shown in the quick demo. So you just go to file preferences and then databases, and there you can register any JDBC driver as long as it's JDBC 4.0 compatible. It should work with Knime. And we have a section on the Knime documentation about the database integration, which explains in detail how you can register this JDBC driver. And then you can use the database nodes as with the other nodes as well. other databases as well.
Okay, so one question was whether it's possible to connect to Amazon EMR or on AWS. Yes, you can. So EMR is pretty much a Hadoop distribution, and it contains all these different services that we've talked about. So it has HDFS, so you can connect to that with the HDFS connection. It contains Hive and Impala, and so you can use the Hive and Impala connectors. Also, it contains Spark and Livy. Livy is a sort of front-end service which wraps Spark into a REST API, basically. And we have a node that allows you to use Spark via the Livy REST API. So that's definitely possible also on EMR because it has Livy inside. Okay, I think in the interest of time, we should move on. Next thing I want to talk about is the Knime extension for Apache Spark. So this extension of Knime is provides a set of nodes that try to cover large parts of the data science cycle. So they allow you to read data into Spark. You can do pre-processing, and due to Spark providing this library called Spark MLlib, we can also do a lot of predictive analytics and advanced analytics on Spark, because all these algorithms for classification and regression and clustering, for example, Spark has them in this MLlib library, and we have nodes that make use of those really scalable and distributed implementations of those algorithms. So the Spark integration offers a relatively large set of nodes. I don't want to highlight many of those, but kind of there's this whole section here that is for data import, so you can read various data formats such as Parquet or ORC or also CSV. And these nodes, they will give you, you have to point them to the file, and they will provide you a Spark data frame then, on which you can use the other Spark nodes. Also, you can read data from databases such as Hive, Impala, or also standard JDBC databases. This is what the DB2 Spark node does. On the left-hand side here are the various ways of connecting to a Spark cluster. And that's something I want to talk about in a little more depth. So essentially, we have 3 nodes that allow you to create or connect to a Spark context. The first one I'd like to mention is create local big data environment. We've briefly discussed this in the questions already. The idea here is that it will run Spark locally on your machine, so you don't need an external cluster, which means the scalability is limited, so it's bound to what your local machine can do, but it's really good for workflow prototyping and also just trying things out. The more kind of production environment nodes are create Spark context Livy. This node connects to Livy, to the Livy REST API, and then instantiates a Spark context using that REST API, and basically drives all the interaction with Spark over the Livy service. And also recently in the 4.1 release, we've added the Create Databricks environment. So on Databricks, usually you have to pull up a Databricks cluster in the Databricks web UI. So this is then already there and running, and this node allows you to connect to this already existing environment and use basically the the thrift server, which is the JDBC front end of Databricks, and also Databricks file system and Spark. All right. As for the Livy node, so this one typically requires a Livy service running in your cluster. So we have that on HD Inside, and the Hortonworks HTTP distributions, they already include Livy. For CDH, we're offering a package. It's called a parcel, which you can just install via your Cloudera manager, and then it will run the Livy service for Knime to connect to. Also, EMR also contains Livy by default. To work with Livy, you'll notice it has this bluish input port that is the file system input port. So to connect to Livy, we need to be able to ship data back and forth between Knime and the Spark context. And the way we do that is via temporary files over some file system. And that's why we have this ingoing file system connection here. And there's a variety of different file system connectors that you can attach to the Livy node. Yeah, importing data to Spark. I think we've covered most of that. So I won't be going into much detail here again. PySpark is a very nice thing we added last year as well. So since PySpark is so popular in the data science domain, we added this little set of nodes that basically have ingoing data frame ports, and then you can type Python code that uses the PySpark API to perform computation on those data frames. And you can also do a live preview of results within the node dialog already. I mentioned Spark has this MLlib, which provides a lot of algorithms for machine learning. And we've built a whole set of nodes around that. And the idea here is to keep the usage model familiar to users of the standard Knime nodes. So you'll find that a lot of the dialogues for example, Spark k-means or the tree learner nodes, they will look relatively similar to the standard Knime tree learners. So we're trying to sort of flatten the learning curve for users here. And of course, they require no coding. Yeah, and there's this large set of algorithms that we have. Okay, one thing about the model learner nodes is that they have this special port, this also bluish port here. This one contains the learned model, and there are various things you can do with those models. So you can either use them for prediction right away with either, so the Spark k-means model, for that you would use the Spark cluster assigner. The other nodes that are more classification and regression, they have special predictor nodes. Also, you can look at the model, or you can store the model somewhere where you can read it back in later to do prediction. Okay, this brings us to the second demo I'd like to give. So this is from one of our blog posts. The idea of this demo workflow is to predict demand of taxis in the New York metropolitan area. Again, this is based on a public data set, which we've provided here, which we've included here in the shape of a Parquet file that we're reading in. Here, we're using the create local big data environment node, and if we take a brief look at it, it has a few options. Quite interesting are a number of threads. So if you have a strong machine, you can even bump up that number to make more use of your sort of single node resources. Also, if you don't need the database connection port, you can also switch it off by selecting Spark SQL only in the SQL support section. So the data set is essentially time series data. So it is already a little bit pre-aggregated. So you have hour resolution for the number of trips within the New York area. So this is from a particular data from a particular time frame in 2017. What this workflow then does is that it first splits the data set into a training and a test data set. Here we're doing the split based on timestamp, so everything that all the trips that happened before that timestamp go into the training data set, and all those that happened after go into the test data set. There are other ways you can do this. Of course, we have sampling nodes as well for Spark. The way this is implemented here is using the Spark SQL query node. This one is really kind of a Swiss Army knife. Spark SQL is Spark's own little SQL dialect, which is also quite powerful. And since we don't have a node for everything in Knime, or a Spark node for all the things you can do with Spark, this is kind of the thing that you would use first when there's no special node for the thing you want to do. Okay. Then what the workflow does is since it's time series data which has a certain seasonality, so there are the demand for taxis in New York varies over the days of the week. This workflow, this piece of the workflow tries to find a suitable lag. So the idea here is that since we have hourly resolution and we want to do prediction for, let's say, the next hour, the standard way of doing this is computing a lag where you fold in the demand value from the hour before and 2 hours before and 3 hours and so on into your row, and those then become your features that you're training your model on and then also doing the prediction on. And finding the right number of feature columns is happening here basically. If you want to know the details, there's a whole blog post about it. Just very briefly, so what this does is it computes correlations between the lagged columns, and then based on those correlations, it finds an optimal value that gives you a reasonable number of features. So not too few, not too many. Okay, then basically we're recomputing computing the lagged columns here. So here now we will see a lot of new columns that basically have the lagged values, so that we're lagging on trip count. And then each row contains the trip count from the row before and 2 rows before and 3 rows before and so on. And on that, we're learning a random forest model and then doing prediction on the test data set. And in the end, we can do various things with the models. We can write them out using the model writer node. Of course, we can look at error statistics. So since we're doing a regression here, we have the typical error measures for for numerical data, such as root mean squared error, for example. Also, data visualization. For that, you would have to integrate again with the standard Knime nodes. So if you have data you want to visualize, you pull it into Knime, and then you can use the normal Knime data visualization nodes. So this one is doing a plot with where the y-axis is numbers of trips, and the x-axis is time. And there are two lines in here. The green one is, I think, the actual data, and the blue one is the actual data, and the green one is the prediction. And so we're seeing where, well, it's pretty close. Okay. Going back to the slide deck. Are there any questions about Spark and the Knime extension for Apache Spark? I think now I'll give everyone a little bit of time to ask questions if they have any. Okay, so the first question is Spark restricted to clustering and classification models only? No, I guess not per se. So MLib, so our nodes were basing those on MLib, and so we kind of only can do the things that MLib offers us. The thing is that writing these algorithms is really hard, and not every algorithm is really suited to distributed computation. And MLib kind of offers this relatively good trade-off of high quality implementations of really popular algorithms. That said, there are certainly algorithms implemented in MLib for which we've not made a node yet. If there's something you would like to see, drop us a note. We're open for suggestions there on what you find important or not. But yeah, we're basically, the approach is we've made nodes for all the popular ones. Okay, so if there aren't any further questions, I think we can move on. So there are two remaining items I would like to talk about. And both of them integrate with the Knime extension for Apache Spark. So what they do is they kind of try to add some more pieces that are missing from the sort of standard Spark nodes. The first one is the H2O integration. So H2O is a really nice open source library which provides scalable and really high performing implementations of machine learning algorithms. We're integrating H2O, so we have a dedicated H2O extension, which has a set of nodes. So here you would find, for example, the model learner for generalized linear models, but also really good gradient boosting machine implementation, and a few others that H2O provides. So on their own, these nodes would be local at the moment, so they would run locally on your laptop, but H2O also provides sparkling water, which basically allows you to run all these H2O algorithms on Spark. And for that, we have the create H2O sparkling water context node. So the idea here is kind of similar. It's basically to create an environment where you can use the standard H2O nodes like partitioning, gradient boosting, machine learner, and so on. So these these are nodes from the standard H2O extension, but they require this yellow H2O context input port, and the sparkling water context node provides that. And what happens here is that this will pull up a little H2O cluster inside your Spark cluster, and you can then, using those Spark to H2O and H2O to Spark nodes, you can basically move data frames from the Spark world into the H2O world, and then run the H2O algorithms on them. Also, one really nice thing or aspect of H2O is the Mojo format. So Mojos are files that contain models. It's an H2O specific format for model export. And we also have a set of nodes that allow you basically to write out those Mojos and read them back in, which is really interesting for model deployment. So here what you can do, for example, is you can learn a model on large data inside a cluster. Then you write the model out using the Mojo writer. And then if you're on Knime server you want to do on-demand prediction, you can deploy a little workflow that reads this Mojo, and it has these special nodes, container input, for example, which allows Knime server to export this workflow as a REST service. And so then you can call it via REST with the data you want to predict on. And then it will apply the model, the learned model on that single data row and give you back the result. And the last puzzle piece for the Knime Big Data extensions is the Knime Workflow Executor for Apache Spark. So this one also adds a really nice feature to the Spark extension. The main motivation really is that Knime has all these kind of thousands of nodes that do various things, and they operate on various data types, whether this is images or sound or text data. And for all these things, we have specialized extensions that usually are, in most cases, limited to local execution. So what would be really nice, especially for these kind of pre-processing type of things, is if you could run those in parallel on Apache Spark. And this is what this extension is for. So the Knime Workflow Executor for Apache Spark, with it, you can basically wrap your pre-processing steps in these component nodes. If you need to structure the inside of that component in a certain way. So it needs to have this ingoing data frame and outgoing data frame. And inside, the first thing you do is Spark to table. So you would, in normal execution mode, this would download the data from the cluster into local Knime, where you can apply all these different nodes. So this set of nodes here are text mining nodes. So stemming, tag filtering, document vector computation, and so on. And what the extension offers is that you can switch the executor on that component, and then this little component workflow will run on Spark. So this sounds a little bit magic, but I think it's worth talking about use cases and limitations here. So the way this works essentially is that Knime will upload these little component workflows into the Spark cluster and distribute them over the Spark executor. And then each of these copies will be executed on one partition of the data frame. I mentioned already that in the beginning that data frames are partitioned. So they have this natural kind of split structure. So the Knime workflow executor for Apache Spark will kind of run a copy of this component workflow for each partition, and that means it's good for certain use cases. It's really good for these kind of pre and post processing steps. It's good for predictor nodes and also nodes that are streamable. Or more conceptually, it works with nodes that can operate row by row. What it's not really designed for is to run nodes that need to basically read the whole data set. This is typically something you have when you're doing aggregations, such as the group by node or the joiner node, but also the standard Knime modeler nodes fall in that category. To produce a useful model, they need basically either to see the whole data or especially crafted subset of the data, which was derived by proper sampling. This is not something you have with the partitioning. So the partitioning in Spark is really only a means of parallelization. It's not inherently designed, to provide a kind of a subsampled data set, really. Okay. So this concludes the Big Data workshop. Thank you all for attending and for your patience with our technical problems. I apologize deeply. I hope you could enjoy it anyway, and yeah, stay safe. If you have any further questions, you can still ask them. We'll leave the call open for a few more minutes and answer questions as they arise. Thank you very much. Bye-bye.
Yeah, maybe I can answer one of the questions. So one question was that in production environment, is it possible to schedule workflows? So what you have seen so far is that, or what Björn has used is the Knime Analytics platform. So everything you have seen is part of the free and open source Knime Analytics platform that has no restrictions or anything. So you can use it also in production, but you will need to trigger the workflow execution manually. But Knime also offers the commercial Knime server, and the Knime server allows you to put these workflow much easier into production by allowing you to schedule workflows on the one hand, but it also allows you to share workflows where you have then also versioning and all these kind of things. But you can also trigger the execution of workflows via REST calls. So for example, if based on an event, if a customer comes to your web page, for example, then the web server can trigger a Knime workflow that does a good or bad customer model prediction or something like this and sends the result back to the web server that can then decide based on the result of the Knime workflow what advertisements or something like this should be displayed, for example. So yeah, you can schedule workflows when you have the Knime server. Maybe I take another one. Do we need R installed for H2O? No, as far as I know, you don't need to install anything. Knime takes care of also deploying the dependencies that H2O needs on the cluster. So you simply need to execute the nodes, and then everything is done magically in the background for you. Then another question is, can we run multiple models at the same time for comparison? Yes, you can do that, but these resources will then compete on your big data cluster for resources, of course, right? I mean, if you have then Spark models running in parallel, then these will compete for the resources. But in Knime, there is no limit to that. So if you have parallel workflow branches, for example, they're executed in parallel. So there's no restriction to that. Is Knime server? Okay. Good question. Is Knime server available on premise? Yes. So Knime server is available on premise, but also we provide ready marketplace images for Amazon Marketplace and also Azure Marketplace. But of course, you can install it also on premise, and it runs on Linux and Windows. Do we need a licensee for workflow executor for Spark, Apache Spark? For the preview, you don't need to have a licensee to use it, but we are still not sure if we will make that available for free or if that will require a licensee once it's production ready.
Also, if you happen to have an interest in Knime workflow executor for Spark or want to discuss usage options for your use cases of that, you can drop us an email to bigdata@knime.com.
Yeah, and if you are looking for a node or a workflow or something like this, we can only warmly recommend the Knime Hub, which you can reach at hub.knime.com, and then simply type in there what you're looking for, and then you should find a workflow or a node that will help you to solve your problem there.
Okay, so it seems there are no further questions. Again, I would like to thank you for your attention and conclude the webinar at this point.
Thank you.